Hello and welcome to Tribe Topper. In this video session, you are going to learn about magnetic field due to a current carrying conductor. So, what are we going to talk about here is uh, Orsted's experiment. So, Orsted was a scientist who was performing an experiment, and what did he find? That when current is passed through a wire, like here you can see there is a conductor and this is a current carrying wire, and around this conductor a magnetic needle was placed. So what Orsted found out, that the moment a current starts flowing through the conductor, the magnetic needle gets deflected. So magnetic needle deflects when current passes through the wire, right? And another thing that he noticed, that if he reversed the direction of current, the magnetic needle deflected in the opposite direction. So the direction of deflection of the needle reversed, the direction of deflection of the needle reversed on reversing the direction of current. And third interesting thing he noticed was that if he passed greater amount of current, the deflection in the needle was also higher. So the extent of, or I would say degree of deflection of the needle, right? The degree of deflection in the needle was higher for larger current. And obviously there was no deflection if there is no current flowing. You stop the current, the deflection in the needle stops. Now the thing is that a magnetic needle, it deflects only when there is a magnetic field around it. Otherwise that magnetic needle just keeps on at rest. It will seek its north and it gets affected by the earth's magnetic field, and finally it comes to rest. But if it is lying at rest and you have a current carrying conductor around it, the needle suddenly deflects, which indicates the presence of a magnetic field. So this led Orsted to conclude that whenever a current carrying conductor is placed somewhere, it produces a magnetic field around it. So this was Orsted's conclusion from all these observations. So these were his observations. And what was the conclusion? So the conclusion was that a current carrying conductor produces a magnetic field around it. So we can also say that a current carrying conductor behaves as a magnet. Like if we talk of a solenoid is something like this, like a long wire tied in the form of a helical spring over a soft iron core. And then what happens, that this current carrying wire, this solenoid, will have, this is the current flowing through it, and it will develop the north and south polarities around it. And you can remember that which polarity will it be, the north or south. So we have it like this. This is, if you look at a loop, like this is a loop, if the current in this loop is flowing anti-clockwise, then this is going to be north pole, and if the current in the loop is clockwise, then that behaves as the south pole. Now if you look at this, so for a person standing here, the current is flowing like this, so for him the current is going clockwise, so this side of the solenoid will behave as the south pole. And for a person standing here, when he looks at this, so the current is flowing anti-clockwise, right? So that means for this side the person will appear as the north pole. So this behaves as a bar magnet. So this is important to remember, that whenever you have a current carrying conductor, it will produce a magnetic field around it. That means it will behave like a magnet. And the If it is a loop, then you can look at the loop that anti-clockwise current will be the north pole and the clockwise current would be the south pole. And in general, to find the direction of magnetic field due to a current carrying conductor, which is of course a straight one. So all you have to do is you can try that with by holding a pen. So hold your pen in the right hand and put your thumb parallel to the conductor or pen like this. So if the thumb indicates the direction of current, then the curl of these fingers is the direction of the magnetic field. And as you can see that this thumb indicates the direction of current vertically upwards, the curl of the fingers is anti-clockwise. And if I just simply reverse this down, so you will see if we reverse it down, the current now is downward and the curl of the fingers goes anti-clockwise. So, no, this goes clockwise, sorry. This goes clockwise. So that means if the current is in the upward direction, you will have the anti-clockwise loops, and if the current is in the downward direction, you will have the clockwise loops. So when they give you a question, you have to recognize it like if there is a dot here in the center, that means the current carrying conductor is a straight conductor and the current is leaving the page towards you. So it is coming out of the page like this, upwards. So this dot indicates current towards you. And if it is like an arrow, or this, so this tail of arrow, that indicates the current is entering the page away from you. So that is a straight conductor holding the current inwards. So dot will be indicating the current outwards, so you will have the anti-clockwise loops, circles. And for current where you have this cross, that will indicate the current is entering the page away from you, and you will have the clockwise loops. And that's all in this video session. In the next video session, you are going to learn about the force acting between two current carrying loops. Thank you.